Well, hello, chemistry. Here we are, ready for Chapter 9, Stoichiometry. And you're probably wondering, what the heck is stoichiometry? Well, stoichiometry is the quantitative analysis of chemical reactions. Well, what does that mean? It means that we're going to be looking at amounts and values of reactants and products. So instead of just talking about the reaction, this is taking place or whatever, single displacement or whatever, we're going to talk about quantities, mass, how much carbon dioxide is going to be created when you burn your gallon of gasoline. So stuff like that we need to know. So super useful, real important part of chemistry is figuring out these actual quantities. Take a scoop of something, what's it going to really mean? So starting off here, and I'm going to try to go through things a little fast so I'm not taking up too much time. So first thing you always have to have with for stoichiometry is a balanced equation. So we've been balancing equations like this and going through, and as you're looking at the numbers of these and thinking, well, what do we have to do to balance this? So I got an odd number of hydrogens here, so I'm going to have to double this and make that an even number. Well, that gives me 2 sodiums now, so I got 2 sodiums here. I've got I just fixed the hydrogen. 2 here and 2 there makes 4 hydrogens. So if I go like that, that gives me 4 hydrogen and 2 oxygens. And hey, I got 2 oxygens there. So now we have a balanced equation. So when you think about this balanced equation and what that really means, what do those coefficients mean? We're talking about like atoms and molecules. And so we got 2 atoms of sodium reacting with the water, and we get 2 molecules of sodium hydroxide out of it, and 1 molecule of hydrogen. Remember, that's what blew up when we put the sodium in the water, was the hydrogen. So these numbers here are talking about, we did this with the models. You need to put stuff together and it all is going to work out. Now, to make this a little bit more useful, though, when we look at a problem like this, carbon monoxide reacting with oxygen creating carbon dioxide. So we look at the ratios here, 2 to 1. 2 carbon monoxides for every 1 oxygen molecule here. Well, another way we could think about that is it being dozens. If I had 2 dozen carbon monoxides and 1 dozen oxygen molecules, I would make 2 dozen carbon dioxide molecules. So when we think about the quantities, we're not just talking about 1 atom of this, 1 atom of that, putting them together. We got to have billions of these and billions of those. So we're looking at the ratio. Well, most of the time we're going to be talking about moles. When we talk about quantity in chemistry, we're talking about moles. So just like a dozen, it's a set amount, remember? So a dozen's always 12. Well, a mole is always 6.02 times 10 to the 23rd. Foo. But that's trivial. Who cares about the number of atoms? I don't care. I just want to know the connection of how much of this to how much of that I'm going to need. And the reality is I need to really get into grams, because I'm going to take a scoop of something, and I don't know how many atoms there are, but I can measure its mass, and then I can figure that out. So the practical part is really when we get into the mass. But when we talk about these balanced equations, really what they're telling us is the molar ratios. How many moles of one thing compared to moles of the other thing. So here's a good example. We got silver sulfate reacting with potassium phosphate, and we get potassium sulfate, which is aqueous, and silver phosphate, which is a solid. That's going to be our precipitate. So we do have a chemical reaction. We have a double displacement reaction going on here. But the first thing we always have to do when we're doing stoichiometry, make a balanced equation. So these are my balancing. You can look at the numbers and figure that out for yourself. But now I know the molar ratios. And that's the important part. So when I look at doing this and taking to figure out, well, if I have 12 moles of silver sulfate, we know it's a 3 to 2 ratio, right? And when we think about, well, one way you can look at this is, well, if I'm going to 12, how much bigger is that than this 3 that I started with. And you say, well, it's 4 times bigger. Well, if I'm starting with 4 times more stuff, I'm going to end up with 4 times more stuff on the other end. And so 4 times more should be 8 moles of silver phosphate. Well, this is pretty easy because I made easy numbers, so you can just kind of think it through in your head. But most of the time, it's not going to be easy numbers. And, what if you had 10? It's not going to be a nice even number. You have decimals, you have to work it all out. Well, here's how you work it out. Always start with your given. This was my given value, 12 moles. Now, don't just put moles. Moles of what? Put the silver, it's silver sulfate. And that's what I'm starting with. Now, I'm going to use a conversion factor. Remember, conversion factors are equivalences, these ratios to each other. And so I know that up here, for every 3 moles of silver sulfate, I'm going to get 2 moles of silver phosphate. That's my molar ratio. Well, what do I want on the bottom? I want to get rid of the silver sulfate. So I put moles of silver sulfate on the bottom. And what I want to get is moles of silver phosphate on top. So you can imagine if I didn't put these in here, I'd just have moles over moles and moles here, and you can do whatever you want with those ones, right? And so this is going to be specific. You have to have the moles of silver sulfate on the bottom. And I looked up my ratios, my balanced equation. I have 3 here to 2 there, 2 to 3 ratio. So when you're looking at this and looking at your units, moles of silver sulfate crosses out. I'm left with moles of silver phosphate. And do my numbers. 12 times 2 is 24. Divided by 3 is 8. Now, we do need to worry about significant figures. We're talking about measurements here. Somehow somebody measured out these moles, so these are significant. I have 2 significant figures here. These, though, the balancing of this, there's no significance in that. I didn't have to use a device or anything. I'm just counting things. And counting things, there's no error in that. So we don't worry about the significant figures with the counted numbers. So my answer needs to have 2 significant figures. So my answer should be 8.0 moles of silver phosphate, like that. So, let's try another. When we think about these molar ratios, it's just like if you're dealing with something like a car. What's the recipe for building a car? Well, you need 4 wheels, you need a chassis and a motor, and then that will make 1 car. Well, if I had 12 wheels, how many cars could I make? Well, you think I need a group of 4. How many groups of 4 are in 12? Oh, there's 3 of them. So there's 3 groups of 4 in here. That's what I need there. So I'd have to have 3 chassis and 3 motors to make 3 cars. Well, what if I gave you a different piece of information? What if I told you I had 120 kilograms of wheels? Well, the ratios here, this 4-to-1 ratio, wheels to chassis, is not by mass. The wheels are not 4 times heavier than the chassis necessarily. They might be, maybe if you had some big giant monster wheels and a tiny little chassis, maybe that would be 4 times the amount. But for most cases in most cars, the wheels are much less mass than they are the chassis. But these numbers, 4-to-1, is talking about quantity. So to figure this out, how many cars can I make from 120 kilograms of wheels? What do you need to know? That's right. You need to know the mass of each wheel. So one wheel is what I should have said there is 10 kilograms. So let's say that's the case. So if a wheel is 10 kilograms, well, to do my math here, I would start with my given. I have 120 kilograms, and my ratio is I want to get rid of kilograms, and I want to get wheels. Right? So 1 wheel is 10 kilograms. That's what this ratio, this equivalence is telling me. So I see my units crossing off here, and 120 times 1 is 1, divided by 10 is 12. So I know I have 12 wheels I could deal with. Now I could go back to this part of the problem like I just started with and figure out how many chassis I need and motors and all that stuff. So the key thing is we got to know quantity to work this stuff out. Knowing mass, we need to change it first. So little review here real quick about molar mass. Remember, molar mass is the same as the AMUs, the numbers that we see on the periodic table. When we talk about a mole of it, it's going to be that many grams. An individual atom of magnesium is 24.30 or 31 AMU. But if I have a mole of it, it's going to be 24.31 grams if I have a mole of it, right? We don't really care about this stuff over here, the number of atoms. That's trivial stuff, you know, and we're not going to really worry about that. We're just going to keep things in moles and really get to the practical part of being in grams. So when we look at this mapping here, this is a very useful tool. A lot of people like to write this out when they're working on problems, just kind of help figure out where you're at and where you're starting, where you're ending, what step you're on right now. So when we look at this, the most important part, you see how I have this stuff blue and this stuff red. That means this is one substance over here, and this is another substance. To bridge this gap between the two different substances, I need to talk about moles. I can't talk about grams of something and compare it to grams of something else. I need to know the ratio of moles for that reaction. So this molar ratio that I get out of this, the conversion that I'm using here, I'm going to get that from the balanced equation. That's where I'm going to get this molar ratio. How many moles of this to how many moles of that? Now, just like I did with the wheels, if instead of knowing the moles of the reactant I started with, if I knew the grams, I would need to change grams into moles. Well, how do you do that? You use the molar mass, which is, and where do you find that? You find that number on the periodic table. Okay? Now, when you get over here and you figure out how many moles of the product you've made, then to get into grams, we also need to use that molar mass, and again, we're going to get that from the periodic table. So those are the tools that you need. You need the balance equation always, because we're always bridging this. That's bare minimum. We're going from moles of A to moles of B. But the biggest one we would have would be starting with grams of A, going using the molar mass from the periodic table into moles of A, balance equation to moles of B, and the periodic table grams of B. So 3 steps, 1, 2, 3. Now sometimes you might be starting here, moles of A, and going to moles of B, and getting into grams of B, and ending here. Well, that would be a 1, 2-step process to get that done. So let's try some out. So we have combustion of methane. So if I want to know how many grams of water are produced from 4 moles of methane burning, well, the first thing I have to do is have a balance equation. So to balance it, maybe, there we go. That's what we need, our coefficients there. And now to do my work, I need to start with my given. Here's my given value, 4.0 moles of methane. Well, I want to get rid of moles of methane, so I'm going to put that on the bottom. And I want to get moles of water, because moles of one to moles of the other, right? So I'm going into water, and where do I get that ratio? I get it from the balance equation. It's like there's a 1 here, right? So 1 of these to 2 of those. Now I'm not done, so I'm not going to stop here. I'm going to keep tacking on another conversion. And so I want to get rid of moles of water. Whoops, H2O, and get grams of water. So how do I find that number out? Well, this is where you're using the periodic table, and you would take the water, 2 hydrogens. So we'd have 2 times 1.0079. That's the molar mass of water. We have 1 oxygen from the periodic table is 15.99 grams. and we would end up with 18.040148 grams per mole. That's the molar mass of water. That's the number that's going to go here, 18.0148 grams. Now, to finish this off, I see my moles crossing off, moles of water crossing off, and I'm left with grams of water, which is what I wanted. So on my calculator, grab your calculator, 4 times 2 times 18.014 gives you 144.1184, blah, 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 some more there. We need to worry about significant figures, though. We're talking about measurements, right? We have 2 significant figures there. We don't have any here. These are just counting. Somebody had to figure out the numbers here, so that's 5 there. So I need to go with the least amount. So rounding my answer, it should be 140 grams of water would be produced. So let's do another one here. We can relate any 2 things here from this balanced equation. This time let's relate methane to carbon dioxide. So again, I'm going to start with my given. I've got 150 grams of methane. So the first thing I want to do is I want to get rid of grams of methane and get moles of methane. So counting those up from the 1 carbon, 4 hydrogen, that should be 16.0426 grams for every 1 mole. Remember, it's always 1 mole when we're talking about molar mass. Well, my second step, now that I have moles of A, so that was grams of A to moles of A, now I want to go from moles of A to moles of B. So what do I want on the bottom? I want moles of methane on the bottom, and I want to get moles of carbon dioxide on the top. And we get this from the balanced equation. We see 1 here and 1 there, so that's a 1-to-1 ratio. But we still need to do this step to make sure everything's working out and our units are working out. So these are crossing off, grams and moles of methane, moles of carbon dioxide. Well, I want that on the bottom now. And I want to get grams of carbon dioxide. So 1 carbon, 2 oxygen. From the numbers from the periodic table, you should get 44.009 per 1 mole. So that means, as we're going through this, 150 divided by 16.0426 times 1, whatever, times 44.009 gives us an answer of 411.48878, blah, 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 blah. But again, with significant figures, how many significant figures do we have? And what should our answer be rounded into? That's right. We've got 2 significant figures here. We've got 6 there, none here. These are exact. I got 5 here, so I would go with the least amount, and that makes my answer 410 grams of carbon dioxide. So from burning 150 grams of methane, I created almost 3 times that amount of carbon dioxide. It's kind of crazy, isn't it? Now, just imagine when you're burning octane in your gasoline, how much carbon dioxide are you putting out with that? We can figure it out, and we will. So, should have enough information now to get going on things. So, you can get into the stoichiometry and start working some problems out.